Imagine yourself a member of a team tasked with creating the next generation of spacecraft capable of withstanding the severe heat and pressure of re-entry into the Earth's atmosphere. To accomplish this feat, you must have a comprehensive understanding of heat and mass transfer, notably convection. You can develop thermal protection systems that optimize convection to keep your spacecraft and crew safe on even the most treacherous journeys if you have the correct knowledge and tools. I'm Amit, prepared to dive into the thrilling realm of heat and mass transfer and discover how it can make or break the next major leap forward in aerospace technology. The passage of thermal energy from one body to another as a result of temperature differential is referred to as heat transfer. And there are three types of heat transfer. The first one is the conduction, convection, and radiation. Conduction is a type of heat transfer that happens when a temperature gradient exists within a material, causing thermal energy to move from higher temperature regions to lower temperature parts. In other words, heat is transferred through the material without the material itself moving in bulk. The second one is convection. It is a type of heat transfer that occurs as a result of temperature changes within fluids such as liquids or gases. In other words, heat is transported by the fluid's bulk motion. The third one is radiation. It is a type of heat transfer that occurs as a result of emission and absorption of electromagnetic waves like visible light, infrared radiation, and ultraviolet radiation. Radiation, unlike conduction and convection, does not require a medium for heat transfer and can occur in a vacuum. The movement of mass from one point to another, on the other hand, is referred to as mass transfer. And there are two types of mass transfer. We have the diffusion and the convection. Diffusion is the movement of mass from high concentration areas to low concentration areas caused by random molecular motion. Diffusion takes place in gases, liquids, and solids. Convection mass transfer is similar to convection heat transfer. This is the movement of mass through the bulk motion of a fluid, and there is concentration differential between different parts of the fluids in convective mass transfer, which causes the fluid to move and transport mass with it. Heat and mass transfer can occur concurrently in many systems, and the two processes are frequently connected. Understanding heat and mass transfer is critical for building and optimizing a wide range of systems, including thermal management systems, chemical reactors, and biological systems. But today, we are going to focus on the convection. What is convection again? Convection occurs when various parts of a fluid have varying temperatures, causing the fluid to move in a circular pattern, known as the convection current. When the fluid is heated from below, for example, the warmer and less dense fluid rises, the colder and denser fluid sinks lower to replace it, resulting in what we call a convection current. Now you might wonder, what are the examples of convection that we face in our daily lives? That's a great question. Cooking meals on a stove is a common scenario in which a person experiences convection in their daily lives. When a person lays a pot or pan on a hot stove, heat is transferred to the bottom of the cookware by conduction. The air above the surface of the cookware heats up as the cookware heats up, causing it to expand and become less dense. Warm and less dense air rises while the colder air from above travels downhill to replace it, as we've discussed earlier, resulting in a convection current. There are several examples of convection in aerospace systems. Some of the most common are aircraft engines, spacecraft thermal control systems, rocket engines, thermal protection systems, avionics, and many more. Today, we are going to focus on the thermal protection systems as our main example, and we are going to learn more about it as we progress. Now you might wonder, What are the different types of convection and how do they differ? Natural convection and forced convection are the two types of convection. Natural convection occurs when fluid motion is determined by buoyant forces caused by temperature changes within the fluid. In contrast, forced convection occurs when an external force such as fan or a pump is employed to move the fluid and increase the rate of heat transfer. Now, how do they apply in aerospace systems? Natural convection can occur in thermal protection systems such as heat shields during atmospheric re-entry or ascent when high temperatures force the surrounding air to become less dense and rise. This natural convection can carry heat away from the thermal protection systems, allowing it to operate at a safe temperature. On the other hand, it can be utilized to improve heat transfer and system performance in forced convection. Some spacecrafts, for example, use aeroshells with built-in heat shields and air inlets during atmospheric re-entry to provide forced convection, which helps to move heat away from the spacecraft and prevent overheating. Natural convection's buoyant forces influence heat and mass transfer by increasing fluid mixing and encouraging heat transfer between the fluid and the surrounding surfaces. Heat is transferred with the fluid as it travels, which helps to distribute the heat more evenly and prevents hot spots from forming. This can be useful in a variety of applications, such as cooling systems or thermal protection systems used in aerospace, where heat must be removed efficiently to prevent damage. Heat transfer is a significant aspect in the operation of many aircraft systems. Understanding convection is critical for designing a safe and efficient aerospace systems. Thermal protection systems in particular must be built to endure intense temperatures encountered during air entry, ascent, and other high temperature settings. Convection is one of the principal routes of heat transfer in fluids, and its effects on the performance of aerospace systems can be significant. Engineers may develop thermal protection systems that efficiently move heat away from important components, preventing damage and enhancing overall safety and reliability by knowing how convection works and how it can be maximized. Convection optimization can also increase the performance and efficiency of many aerospace systems. Engineers can eliminate the need for excessive cooling or thermal management by developing systems that properly move heat away from vital components, resulting in lighter and more efficient systems. Understanding convection is important for building a safe and efficient aerospace system because it helps engineers to effectively manage heat transfer and prevent overheating while also boosting system performance and efficiency. We've discussed heat transfer and its three types, which are the conduction, convection, and radiation, and the mass transfer, which are the diffusion and convection. We've paid more focus on convection, which happens when different portions of a fluid have different temperatures, resulting in a circular pattern of fluid movement. We've also talked about natural and forced convection and their roles in aerospace thermal protection systems. Natural convection is created by buoyant forces caused by temperature changes within the fluid, whereas forced convection is caused by internal force moving the fluid at increasing heat transfer rates. Natural convection's buoyant forces improve fluid mixing and heat transfer, which is beneficial in a variety of applications, including thermal protection systems used in aerospace. That is all. Let's continue to push the boundaries of what is possible and explore the great frontier of space.